We're just going to really get sort of a start on it. We're not going to be able to go so far that we'd cover everything about nuclear chemistry you could learn, okay? Mostly this is for your ability to understand things like carbon dating, etc. Okay, bud. Fantastic. Yeah, you can actually... Whoop, you okay?
Yeah, don't worry about that.
Okay. We'll have to get towels and stuff later. Okay. All right, so there is unstable nuclei. An unstable nucleus is going to spontaneously emit small particles of energy. This is called radiation. It will do so to become a more stable nucleus eventually. Okay? That doesn't necessarily... Yeah?
So would this whole thing be section 5.1?
Well, it's chapter 5, and you can section it however you'd like. Okay. Yes, it would cover section 5.1 in your book. Those are the corresponding numbers. Okay, so, again, this is going to go towards a more stable nucleus eventually. That does not mean that it necessarily goes straight into a stable nucleus every transformation. Okay? Okay, so natural radioactivity. Most naturally occurring isotopes or elements up to the atomic number 19 are going to have stable nuclei. Elements with atomic numbers 20 and higher usually have one or more isotopes that will have unstable nuclei, in which the nuclear forces cannot offset the repulsion between protons. Remember when we were talking about those nucleuses? They're composed of neutrons and protons, right? Protons repel each other, don't they? So you may have been wondering, why don't they just blow up? And the answer is, sometimes they do. When it's a particularly unstable arrangement. Okay? Now, typically these are overcome by what is referred to as the strong force. I'm not going to go into that in a lot of detail. If you'd like to learn about it, you can either talk to me or there's actually some really good videos online. But yeah, we don't have time to go into that much detail. A little footnote here is the atomic number 19 and below. There are radioactive elements in there. Okay? And not every single one of these has a radioactive isotope that's a significant amount of the naturally occurring isotopes. Okay? So when we're talking about these, it's just an overall trend we're talking about. Okay? An unstable nucleus is going to be called radioactive. It means that it spontaneously emits small particles of energy. These are called radiation. And it does that to become more stable eventually. Okay? Now, if you see the word radioactive here, what does that say to you? It's active with radio signals. That's what that is, okay? It literally, that's why that got named like that, is they'd have these substances, they'd bring them near a radio, and it would actually develop static on the radio, okay? And so you'd have like this rock, and it would be radioactive. All right? And so that packets of energy, they can be things like a helium nucleus. They could be things like an electron. But they could also just be electromagnetic radiation, i.e. light. Okay? And you all probably have this idea in your head of radioactive substances emitting light. Is that true?
Yeah, the green glowy thing.
Yeah, the green glowy thing. Who here has seen The Simpsons?
Yeah. Doesn't that only apply if they've absorbed some form of energy, though?
No, they'll give off energy on their own, but most radioactive substances are not actually glowing in the dark. It's actually fairly rare to get radioactive substances that would glow in the dark because most of them are not visible to human perception. Yeah. So if they would give off any light, it would be in frequencies you can't see. Okay? And some of them don't give off basically any light. However, that was a really low number that had seen The Simpsons in some way. So apparently not a good example of things. Okay. Again, so radioisotope, this is going to be an unstable nucleus. It's going to emit radiation. It can be one or more isotopes of an element. It will include a mass number in its name to differentiate it from the non-radioactive isotopes. Everybody see the periodic table and look up at lead. See that? Okay. Everything below lead basically only has radioactive isotopes. Okay? Lead is the last one on the periodic table that actually has stable isotopes. Everybody see the ones with the little, like, their outlines of the names not filled in? Okay, anybody know what that is? Those are man-made ones. Okay? We have not found those in nature. That's not to say that they could not exist in nature, but they'd exist under extreme conditions. Because they'd have to have things colliding together to force them to be made. Okay? So it'd be pretty crazy to find
What
them.
are those that are like the dashes? 89-103?
What do you mean by dashes?
With,
Yeah, those are, remember how the bottom part actually is supposed to be inserted in there. So the dashes are telling you it's that bottom part. And if you look closely, it actually, you can see that it goes from those numbers to that number. See that 89 to 103? Yeah, you got it. Some periodic tables, by the way, the ones that aren't filled in are actually dashed lined for their letters. That's why it's like, this one didn't have dashed lines, did it?
Are there any elements only found in space?
So far, I don't even want to say. Like, there are things that we have only found by looking at radio signals in space, or we have made. But I don't know if they've ever found elements that we haven't found on Earth that we've only found in space. However, that may not be, that probably, there is elements probably that you can only find in certain, like, star conditions and stuff. That's actually quite likely. The problem being they'd only exist for short periods of time and then they'd radioactively decay for most of them. So we may not actually know what we're looking at when we look at them. And a lot of them, the way we would detect these spectroscopically on a distant object, we wouldn't have been able to run those tests because it only existed for like 2 milliseconds ever. Yeah. So, yeah, actually, there's quite likely there is, but I don't know that they've ever found something. Okay, so this right here is an example of some stable isotopes right here and some radioactive isotopes. We can see magnesium there. So it has this stable isotope, which has a mass 24, and then it has the radioactive isotopes that are 23 and 27 for mass. And you can think of those as like unstable arrangements. Everybody's been stacking stuff, and all of a sudden it slides apart on you and collapses, right? Yeah. Sometimes a can shoots out at you. Sometimes it just makes a loud bang sound, right? Okay. It's a very good analogy for radioactivity. Okay? Okay, this right here, by the way, is uranium. Uranium does not have any stable isotopes. All uranium is radioactive. Okay? Anybody ever heard of depleted uranium?
I feel like that's your back to the future.
Yeah.
Actually, we used it in ammo rounds. We've actually made the entire Middle East radioactive, very detectably so, by shooting depleted uranium shells at things in the multitude of wars in the Middle East.
No wonder there's so many extremists popping up. Their heads must be getting us good badly.
Well,
Is it possible that all the radiation has started decaying their DNA? That happens with radiation if it's exposed for too long. Right?
Not really. Very likely no. That it's not having any serious effects other than a slight increase in cancer rates. Most mutations don't take. Most mutations actually don't develop to a full fetus.
Body rejects them.
No. The fetus just doesn't develop. Yeah.
Rather than be born wrong, it's not born at all.
I mean, anyways, so iodine here, iodine 127, and this is iodine 125 and 131, and those ones are the radioactive, okay? Okay, so radioisotopes, they emit radiation like an alpha particle. This is the alpha symbol, so alpha particles. They're identical to a helium nucleus. So you can literally label them as a helium nucleus, mass of 4, 2 neutrons, or 2 protons, 2 neutrons, mass 4. Okay. The difference between an alpha particle and a normal helium nucleus is it's being shot at a little bit of speed, and it doesn't have any electrons on, because it got ejected from the nucleus. It didn't have time to pick up electrons. Okay. And so when you look at an alpha particle, it's basically just going to be the nucleus, no electrons. Okay? A beta particle is an electron. Okay? It is a high-speed electron, high-energy electron. You shot it out of a nucleus. It has considerable speed and energy behind it, but it's an electron. Once it gets stopped, it'll just be a normal electron again. Positrons, these are antimatter. Everybody heard of antimatter before?
Yes.
Yeah. Okay. And it, like, super common in sci-fi, right?
I was shocked to hear that we're actually capable of making it.
Oh, yeah, we do it all the time. You're doing it right now. All of you are making antimatter right now.
No, I mean like in concentrated amounts. We do that in laboratories.
Oh, yeah. Yeah. I mean, not super concentrated amounts, but yeah, we make antimatter.
I don't really understand why. I mean, yeah, the stuff seems awesome, but it also seems insanely dangerous.
Not really. It's being made all the time. So, positrons are the beta plus, and so you can represent them as a positive electron. So this is 0 over plus 1, right? Because it has a positive charge, and it's an electron. Now, the positrons are literally just the oppositely charged electrons. That's it, okay? They have a mass the same as an electron. They have a charge that's just the opposite charge from an electron. Now, it is true that antimatter, when it comes into contact with matter, so if you have a positron and it impacts with an electron, they annihilate each other and produce energy. Okay? If you were to have like milligram amounts of antimatter and let it get in contact with matter that could annihilate it, it would be like setting off a nuke. Okay? It would produce a tremendous amount of energy very quickly. However, on the scale of an electron, there's not enough mass there to really do anything. So it does a little burst of energy. We can detect that energy burst, but it is minuscule. Okay? Anybody ever heard of a PET scan? PET scan? Okay. First off, completely moronic way of saying the name. It should be said PET, no scan. Do you know why? The last word is tomography. Tomography is a type of scan. So that's like saying positron emission, scan. Which is the same thing people do all the time with PIN number, right? PIN number. I'm saying personal identification number. It is really stupid.
Okay, I kind of feel dumb now.
Everybody does it
Yeah.
because it feels wrong not to, right?
Yeah.
Yeah. And PET scan, like if I just said PET to you, none of you would have known what the hell I was talking about, right? And so it makes you feel stupid. And it is kind of stupid, but it's the way to communicate. Anyways, PET scans is positron emission. That's the first P and E. And so they literally shoot positrons, antimatter at you in a kind of weak beam, and then watch it annihilate your electrons. That's literally what they do when they do a PET scan. And so, I know, you've all been shot. Many of you have been shot with antimatter. Okay? Exciting, wasn't it? All right. So, pure energy, i.e. electromagnetic radiation, i.e. light. This is gamma rays. This is just the high energy light, right? Remember our electromagnetic spectrum we looked at? And on the high energy part, there was gamma rays. Yeah. Denoted by this Greek letter gamma. And it has a 0, 0 because it doesn't have mass, it doesn't have charge, does it? Nope. This gamma rays is very analogous in our analogy of when things collapse around you in your everyday life, they make sounds, right? That's energy being released. In our everyday life, it's being released as sound, isn't it? These would be the nuclear equivalent, okay? So when the nuclei collapse to lower energy states, they're going to release gamma rays to get rid of that excess energy, okay? Okay. So this is the alpha particles here. So it's identical to a helium nucleus. It has 2 protons, 2 neutrons, has a mass number of 4, has a charge of 2 plus, low energy compared to other radiation particles, and overall usually not dangerous. Okay. Beta particles, this is going to be a high energy electron, high energy for an electron, that is. It's going to have a mass number of 0 and a charge of -1. Mm-hmm.
Wait, can you go back? I didn't get the stuff about the alpha particles yet.
Okay. What I would recommend is when you guys take notes, don't try to write every single thing.
Can you just
Print those out from my PowerPoints that are online.
I find writing it helps me remember. Can you just
Okay.
tell me what's essential to know from this then?
I mean, I'm giving you the essentials. It's already distilled down from the book. It's just that a lot of this is not stuff that you need to write out during a lecture, where you need to concentrate on understanding the main thrust of the material. You would want to take this information, transcribe it into notes on a flip cards, so you could study and get a better idea of the memorization of it.
So essentially, we can just print it off, and there's no point in actually writing it.
You can print it off. What you want to do in note taking is you want to write down things that will help you understand the material. Okay? Writing down what's in my PowerPoints is sort of the worst way to take notes, because it's not going to get you a lot.
Alpha's not dangerous for the most part, correct?
Alpha is not dangerous for the most part, yeah. Yeah.
But beta is.
Yeah, beta is higher energy. It's more penetrating. It's usually more dangerous when you're exposed externally. So this is going to form a non-stable nucleus when you need to have a neutron that changes into a proton and an electron. Think of it like this. This is how you take a neutron and you lose a negative charge, right? If you lose a negative charge, what would that leave you for charge? Positive. So it's how you take a neutron and transform it to a proton. Okay? And that's that. Okay. By the way, if you guys would like, I can post a video talking about note-taking and how to do the Oxford style of note-taking. Okay. Okay. So positrons. Positrons will be a beta plus. This has a mass number of 0, has a charge of +1. Again, it is the positive electron. Fairly easy to remember because electron, the tron part, see that? Positron, positive electron. Okay. Again, it can be denoted several different ways. The positron can be denoted as a positive electron. The other way you can denote this is a positive beta particle. Now, the difference between electron and beta particle is just that the beta particle, you're just expressly saying this got shot out with a lot of energy behind it. Okay? Now, this is going to form an unstable nucleus when you need to go from a proton to a neutron. Okay? So you have a proton, it's positively charged. You shoot a positron out. Now it's lost its positive charge. Still has about the same mass. Not a big difference. And so you end up with a neutron. Okay? So again, this is the process of going from a proton to a neutron, right? You will note, by the way, if you sort of think about this, that hey, we lost mass going both ways, didn't we? Okay, this tells you like some fundamental crazy stuff about the universe. Like antimatter doesn't count the same towards mass. And so there's some crazy stuff going on here. But we can't get into it. It's just a too advanced topic that would just confuse things. Okay? However, yeah, we're doing some funny stuff with the math here. Okay? Okay. So gamma rays, this is going to be high energy radiation. It's going to have a mass number of 0 and a charge of 0. So again, this is your gamma rays. You don't actually have to put the mass and charge numbers for a gamma ray because everybody knows it's light, and so it doesn't have those things. Okay? So it's going to be the form of energy it's emitted from a non-stable nucleus to literally just lower the energy of the nucleus. Okay? So your arrangement of protons and neutrons was unstable. They shifted. Now they're more stable. Okay? And we release the gamma. These are the forms of radiation summarized on a table. That table's in your book, and it is also on my slideshow. And so if you want to summarize all that information so you can better understand it and memorize it if you need, that's that. Most people are probably not going to separately need to work on this memorizing it because the homework will basically take care of that for you, right? Okay. So let's give the mass number and charge of each type of radiation. Okay. And go ahead and please take the QR code for that. It should come up with the question there as well. Let me know if that works. Okay. And it's a little quiz. Does it show you the question in the quiz?
I don't see it. It just says
25 users have joined.
Did you set the limit for how
Oh,
many
it
people are
tells us all
supposed
of
to join
those
before
out
it
there.
starts?
So the limit is 50 people at once.
Well, then it might wait till we get 50 joiners.
No. It doesn't. It shouldn't wait for 50 people. It will just. It should just give you the quiz. Okay. Okay. Oh, there we go.
And it was there for
Okay.
days back.
I don't know why it did that like that. That's weird.
Yeah, this would have been the thing that would have been useful to have written down.
Okay. All right. So, alpha particle. What sort of mass and charge does that have?
Class number 4, charge of
Yep, you got it. Mass of 4, charge of 2, 2 positive, negative. Positive.
Wait,
It's positive. So, if we have a positron, mass number? 0. Charge number? Plus 1. Okay. So, if you notice on here, we have two things that now are possibilities, right? The others have been eliminated. So, we go to the next one. We go beta particle, mass number? 0, because it's an electron, isn't it? Charge? Yep, -1 minus. You got it. Okay, the next one is a neutron. Neutron is mass of 1. Very good. And charge of 0. Fantastic. How about a gamma ray? Mass of
0.
Yep. Charge of 0. Yeah.
It's light, it doesn't have.
Okay. And so go ahead and answer. Okay. All right, fantastic. There we go. Okay, and so we got that. That is the correct answer. All right, so that actually worked okay, considering it's the first time. Yeah. How did everybody feel about that one? Eh? Better than Plickers, worse than Plickers?
Better.
Same, better. Okay.
It's almost
Anybody
like
negative?
legit.
Okay.
It's hard to lose.
Yeah, it's hard to lose.
Yeah, that's basically my big issue. Ionizing radiation. So when we have ionizing radiation, what's going to happen is this is radiation that will ionize the stuff that strikes in its path. So when ionizing radiation strikes molecule in its path, it's going to cause those to become ions. If those happen to be something important, then guess what happens? They shouldn't be ions. They're now ions. They're going to cause damage, aren't they?
Yeah.
So if it happens to be DNA, for example, like you're saying mutations, ionizing radiation can cause mutations. And it will cause some increase in the mutations. Now, to be fair and honest, there's other stuff that can also cause mutations. And countries have had a bad habit of mass deploying those things. Including the United States, which has not had quite as bad of a habit as some other places, but has done a few of those, yeah. Plastics probably being the one that has caught the most attention recently, with PFAS, forever chemicals. Yeah. But, like, that's happened all throughout. Did you guys know the receipts, the silky feeling receipts? Did you know those are fixed with a birth control chemical?
What?
Yeah. Yeah, it's a chemical that was sold as birth control in the 1940s. And you touching those receipts actually has a dosage that is delivered to your blood.
Well,
So
Yeah.
you shouldn't put your phone directly in your pocket either, because the radiation.
I mean, honestly, that's actually not really. No. The amount of radiation your phone puts off. Now, honestly, if you're actively like using your phone heavily, that would be a higher amount of radiation. But the type of radiation it's being put off is non-ionizing. It's very low energy, and so it's basically like getting hit by a heat lamp.
Is it the same as wearing an Apple Watch? Or is
Yeah.
it different? Okay.
Yeah. You would need something quite a bit stronger for it to be really threatening.
Okay.
Yeah.
so what kind of birth control, like, is it made out of? In the 1940s, I didn't know there was birth control back then.
There was, yeah. There's been birth control since the Roman Empire. Yeah.
There's always been.
Oh, yeah.
It just came around like 70s or 80s. Like,
China has 6,000 years ago a recorded recipe for birth control, and apparently it was pretty effective.
You know, birth,
So,
birth control isn't just the pills, right? It's a blanket term for anything that controls reproduction.
yeah,
Like
though
condoms are birth control too.
they actually had a pharmaceutical herbal remedy, but yeah, you can also be talking about condoms, which are like 4,000 years old.
Yeah,
Wait, what?
Yeah.
Oh my god.
Yeah.
You know that? I didn't know.
The entire birth control was invented by the U.S., and this is something new, is total bullshit.
Well, thank you for telling me that, because I was like, oh, it's a new thing. My mom's like, there wasn't birth control back in my day. I guess she lied.
She's true. She's telling the truth.
Okay.
Europe got rid of its birth control around the advent of Christianity, kind of by accident. But basically, the people that did herbal stuff had been heavily associated with spirituality and magic, and they got booted out.
Now they make patches.
The Catholic Church was not a fan.
Funny enough, they were a fan enough to adapt most of their religious, like, rituals. But, yeah, for some reason that one didn't go.
So was it a pill back then, or was it like a device? Or?
There were actually pills.
A lot of people
But no, most of them were a herbal concoction that you would take. Some of them were pastes. Yeah,
Yeah.
that people would smear. Anyways, it's a. We went so far off the topic. Okay, so it's going to damage cells that are most sensitive to radiation. Rapidly dividing cells are a big one. So things like bone marrow, skin, reproductive organs, and cancer cells are some of the ones that get damaged the most. But fetal cells are another big one because they have to very rapidly divide, right, to make a whole person. And so that's why the pseudo based on truth myth of mutated babies, right? But like there is a little bit of truth in that. However, the other things that can also happen to a baby, like mercury poisoning and stuff, is such a large threat as well. So
Isn't that like birth defects, like the crab claw hands and like
Yeah.
missing the arm?
most are not radiation though.
Okay.
The vast majority are chemical. Yeah,
Okay.
yeah. Much more likely to be heavy metals or chemicals. But those are some of those. You can have some pretty crazy stuff. People can be born without eyes, or even the place for eyes. Yeah, it gets pretty wild. There actually are also positive mutations that can happen, but the likelihood is very, very low. So, so the normal tissues around, so cancer cells are going to be highly sensitive to radiation. If you take large doses of radiation, you can actually use that to destroy them. Has everybody seen the where they take the cancer patient or somebody with a tumor and use radiation to destroy it? Or is aware of that?
Yes.
Okay. Radiation treatments? Okay. They do that by taking several different beams and overlapping them in three-dimensional space. And that's how they can lower the radiation that all the other cells get and concentrate it more on the cancer area. Okay? So the normal tissue around cancer cells is going to divide at a slower rate. It'll suffer less damage from the radiation, and that damage will be less impactful because normal cells have kill commands they'll be given. So if something like mutates so it would normally die fairly quickly, you just kill command that and you replace it with another cell, right? But cancer does not have kill commands. Cancer is immortal cells. They don't take kill commands. The radiation may cause malignant tumors, leukemia, anemia, and genetic mutations. Very common in radiation-based treatments for to develop things like leukemia, by the way. Yeah, it's the bone marrow, actually. Yeah, yeah. And so that's why that's a danger, is because bone marrow is susceptible to radiation. And so if you give people like let's say we wanted to kill all the cancer, and they have cancer all throughout their bodies, why can't we just like irradiate their whole body? The cancer cells would die off first, right?
But everything else still would die.
Everything else would also die, but that's like chemo. Chemo's just poison.
You're just killing, you're killing
Yeah.
all the cells.
They literally use cyanide for chemo.
Yeah.
Isn't it like, isn't chemo like the type of like cure or whatever that will kill all your like cells, like your
Yeah.
reproductive cells and stuff where
Yeah.
you're infertile?
Chemo will kill
Or is
all
that
your
radiation?
cells. Chemo's just poison.
So chemo's killing every cell in your body,
Yeah.
good, bad, ugly, all.
It's just
Yeah. So
yeah.
basically we give them a cocktail of poisons that the cancer will absorb faster than everything else, and we hope the cancer dies before you die. Yeah, that's chemo. Now, if you target chemo, by the way, your success rate goes into the 99%, even with advanced stage cancers. So if you take a culture of a cancer and then target it with 100 different chemicals mixed specifically to target that person's cancer, your success rate goes into the 99-something percentile. But that's very expensive to do and takes a lot of effort. So it doesn't get done. Yeah. So cancer actually does have a almost blanket cure, but it's just not possible to deploy it for everybody. Yeah. Yeah, and even wealthy people have a difficult time getting it. Yeah. Yeah, it's actually quite hard to do. Anyways, so this is why you can't full body irradiate somebody, because you have things like bone marrow that are also susceptible to radiation. Okay? You won't be able to kill off the cancer without causing more problems. Radiation protection requires a few different things. Paper clothing for alpha particles, lab coat or gloves for beta particles, Lead shield or thick concrete wall for gamma rays, limiting the amount of time to spent near a radioactive source, increasing the distance from the source. So one of the things you can do if you were going to take notes for this, you would want to take notes that are like alpha blocked by everything, okay? And then beta blocked by thick things, right? And you'd want to take notes that are not just a rote copy of what I put, right? Okay, now, so if I have alpha particles being shot at me in a beam, what do I do?
Just stand there.
Yeah. I just take a piece of paper and put it in front of it, right?
Beta blocked by what?
A piece of paper. Or my skin. You might want to put a mask on because if you breathe them in, they can cause more damage if they're inside you.
Okay, so would
But-
it be fair to say beta blocked by organic stuff?
So beta is blocked by anything that's a bit thicker. Like if you had a bundle of paper, it'd block it. A newspaper would block it. A lab coat, gloves, they would all block beta particles.
So anything.
Okay. Just it needs to be a bit thicker.
Anything solid.
Yeah. If it has some decent thickness to it. Your skin will block alpha particles completely. They'll damage your skin a little. The beta particles will actually penetrate a little bit into your skin. Okay? They'll actually penetrate usually into about the fat layer area. Just barely.
Okay, what about positrons?
Uh-huh.
Is there like higher levels of like beta particles that like you need like concrete walls to be safe?
No, not really. Like, I would not sit there in front of a concentrated beam of beta particles. But if you were to say put like a suit on with a little bit of thickness to it, you'd be okay. Okay, and it will damage usually whatever you put in front of it if it was a very concentrated beam. But you'll be okay temporarily. Like you're not gonna stand there and have somebody shoot you with a beta beam, right? You're gonna be like, that was a bad idea. Let's call this. Now, did I miss?
Oh, I had a question. Isn't those like lead bib things at
Mhm.
the dentist to prevent radiation?
Gamma. Yeah, they're to prevent X-rays and gamma.
Okay, and it's protecting like your like.
Yeah, your
torso area.
important parts and your reproductive organs usually.
They don't
Yeah.
cover that.
They should.
They should.
No,
Somebody's
they
wearing
cover
a.
right here.
Oh, then it's undersized.
Yeah, I mean,
Um,
it's where I'm standing. They're like scanning my teeth, so maybe it can't go that low.
Oh! You being at the dentist office.
Yeah.
Yes, that's fine.
Okay.
Because the beam is, you see that plastic part? That's where the beam is.
Oh,
It doesn't
so
spread past there.
That's what I thought. Okay.
Yeah. Yeah. So that's actually it's not even needed. You'd be fine without it as long as they don't screw up and. But it's just a precaution in case the beam got interrupted somehow or you had some problems with the
Did you
machine.
think I was talking about like regular doctor?
Yeah, I was thinking you were talking about the tech.
Oh no.
It's for like an X-ray.
Oh no.
Yeah.
God, no, just for teeth.
So,
Mhm.
alpha's blocked by everything, beta's blocked by anything solid. What about positrons?
So positrons would be blocked just like beta particles by anything solid. And the gamma rays actually need a thick concrete wall or they need lead shielding to block them. And even lead shielding has to have some thickness to it.
Gamma needs
Um,
thick concrete or lead.
Okay, now the biggest thing is, remember whenever you're dealing with radiation, it's a lot like a flashlight, okay? So if I take a flashlight and shine it on something close, what does it look like? Very bright, right? If I shine it far away, what does it look like? Less bright, much more dim, right? Okay, so radiation is similar. When I'm real close to it, I'm going to get a lot of dose, right? If I get further away from it, like 30 feet away, I'm going to get a lot less dose. It's going to drop down a lot, okay? Also, time matters a lot. You guys ever heard of Chernobyl?
Yeah.
Have you ever heard of the elephant's foot? It's where all the radioactive material dumped down, so it's highly radioactive there. There's actually pictures of people literally like going up to it and posing. And I'm not joking, with no protective equipment on for some of them. And most of those people were actually fine. And that's because they went up to it, posed it, and then immediately left. And that's such high radiation that it actually causes like weird artifacts in the pictures. So it's pretty creepy looking actually. But like time matters a lot. If you sit there and let it go at you for a while, yeah, you're gonna have problems. But if you're just like, whoops, I passed by something radioactive, it's much, much less threatening. Okay? Okay, so this right here is some more details of that and sort of what depth it would be able to go in the shielding. These are some different typical sources that you would find that emit that type of radiation. So let's indicate the type of radiation, alpha, beta, or gamma, protection for each type of shielding. Heavy clothing, what would that protect you against?
That would protect you against everything except gamma.
Yep, everything except for gamma, so alpha and beta. Paper,
Alpha and beta.
just the alpha unless you got a bunch of it, right?
Oh yeah.
Yeah. Lead,
Everything.
yeah, everything, you got it. Lab coat,
Everything except gamma.
yep, everything except for gamma, that's exactly right. Thick concrete,
Everything.
yeah, everything, good. Yeah. Okay, so nuclear reactions. This is an example of a nuclear reaction. We're going to have a transformation of one nucleus. It's going to lose something usually, going into a nucleus that has lost some mass or charge, right? Okay. And this is a pretty typical example. Notice that we don't normally look at the electrons in the electron cloud. We can kind of throw that away and just whatever. That was the previous chemistry stuff. And we don't need that for this. Please note that nuclear reactions are actually incredibly easy to deal with. Okay, and you'll see why in just a bit. So this is the process called radioactive decay. An unstable nucleus is going to spontaneously break down by emitting radiation. It's going to be described by writing a nuclear equation. Whenever you write a nuclear equation, it's always going to have two sides. Notice it's called an equation because it's an equation. Okay? It's literally this equals that. Okay? Meaning both sides have to add up to be the same thing, don't they? Okay. All right, so let's go ahead and look at a nuclear equation. So this is a balanced nuclear equation. Your mass numbers on both sides have to equal. Your charge numbers on both sides have to add up to equal. Okay? So notice that this right here is 251 for mass, right? Okay. This is 247 plus 4. Together, those equal 251, don't they? And so your mass has to be 251 on both sides. Your charge, or your atomic number, it was 98 on the reactant side, the beginning, right? And then you went down to 96 plus 2, didn't you? Okay. And that's again 98, isn't it? And so both sides have to equal every single time. Okay. Okay, by the way, the atomic number, again, tells you that symbol right there, doesn't it? Whatever that atomic number is on the periodic table, that's what that element is, isn't it? Okay. Yep. What is particle is that again?
Helium?
That's an alpha.
Alpha, because it's the equivalent to the helium.
Yep. Alpha equivalent to a helium. You got it. Okay, let's practice.
Is that how a lot of them are? They'll split it and have like an alpha particle.
Yeah, they're all going to be where the different decays I talked about. So they'll all be something, they'll emit an alpha particle, they'll emit a beta particle, they'll emit a positron, they may emit a gamma particle. Okay? That's why I started with those, because it's the overall. Now, there is one that we didn't talk about, but we just don't have time to cover everything. So, okay, and so this is an alpha particle. It's going to emit a helium nucleus, i.e. mass 4, charge 2, atomic number 2. So let's go and practice that. Anybody ever wondered why a smoke detector works.
Because of merit.
Yep, because America. Americium, actually. So inside of a smoke detector, there is actually an alpha source, an alpha particle source. This is Americium 241. Americium 241 actually shoots off alpha particles pretty consistently and slowly decays over time. Okay? So yes, your smoke detector does go bad over time. Okay? Not just the batteries, like the whole smoke detector just stops working eventually. What's going to happen here is that these alpha particles shoot over to another side where there's a detector. And that keeps that from triggering an alarm. When you have smoke, the smoke actually captures the alpha particles and they can't go over to the detector. And so that actually triggers the alarm. Okay? And that's how a fire alarm works. Woo! Good stuff. By the way, does anybody know where the greatest concentration of human wealth that has ever existed is located?
At Fort Knox?
It's not Fort Knox, but it's a good guess.
No, wait, hold on. Genghis Khan's tomb?
Nope.
Greatest combination of wealth in human history.
Yep. It is the nuclear waste disposal site for the United States.
You mean to say that our nuclear waste is worth more than all of our assets?
It is. It is.
We're leaving it sitting there.
We are. There's some complicated issues around why we don't go in and recycle those. We are starting to. Like, it is starting to become a thing. But if you were to fully process all the different rare isotopes in that, you would have a wealth that's greater than the actual amount of money that exists in the United States of America. It would be a massive amount of wealth. And part of that's because some of these isotopes are incredibly expensive. Like this Americium 241, pound per pound, is far beyond gold. Okay? You can have a little bead of this and it'd be like having a brick of gold. Right? So these radioactive isotopes are worth far, far more than having gold of its equivalent weight. Weird thing, weird fact, but it is. Anyways, let's do a nuclear reaction for this. So we have Americium 241. We look up the periodic table. We look for Americium. Where should we look on the periodic table? Towards the top or towards the bottom? Bottom, yeah. And that's hinted to us by the fact that the mass is 241, isn't it? Okay, and so we look towards the bottom and we see the atomic number is 95. So the next thing we're going to do is we're going to do an arrow because this has to yield something, right? And we're told that this has alpha decay. See that? Meaning it shoots off an alpha particle, doesn't it?
Yeah.
Okay. And so we put plus, and we do a helium nucleus for 2He. Is there something else we could have put there instead of an He?
Instead of a what, sorry?
Instead of an He? We could have put an alpha. Mm-hmm.
So it doesn't give us the 42Ag. We have to.
It does right here.
It tells you right next to it.
So it'll tell us. We don't have to figure that out.
Yeah, you'd be told the type of decay.
Okay.
If we were doing a much more advanced class, you might have to figure out the decay pathways, but not for this class.
Okay.
What's the name of element in
Neptunium. Yeah, you got ahead of me. But good. Okay, so the next part is going to be, well, we need both sides to add up to be the same, right? Okay, and so we had a 95 over here. For this side to also add up to be 95, we have to subtract off 2, don't we? Because there's a 2 here. And so that's going to give us a 93. The mass number, on the other hand, we had a 241. And so we go 241. And the helium has a mass number of 4. And so we have to subtract off 4, don't we? Okay. Mm-hmm. Huh?
When you add it, you subtract the mass.
Yeah, what you're doing is you have to add up to the same thing on both sides.
So,
And so, okay, so let's put it this way, okay? Okay. You had $95, right? Okay. So you gave $4 to somebody. Now what do you have in your pocket? Okay. Uh-oh. Okay.
It just goes back to balancing the equation.
Yes, it's adding up. It's just balancing the equation. So there's several different ways you can go about these math problems. Mm-hmm.
so you subtract 2 from the 95 first, correct?
Yeah.
And-
Let's step back real quick
Okay.
and just go ahead and talk about how you do math problems where two things add up to the same on both sides, which is all equations, right? Okay. Okay, that's all we're doing here. We have to add up the same side, two things at both sides that are equal, because this is an equation, right? Okay. Okay. So if we start on one side with a 95, right? So we have to have gotten rid of 2, right? Okay. And so when we get rid of something, we have to go down by 2, right? Okay. And so that would be your 93. Another way to look at that is, again, we have 241 that we started with, right? We got rid of 4 of the mass going off into a helium, right? And that means we would have to subtract by the 4, right? Okay. And so minus 4. I don't want to... It's not going to help you to make it into a hard rule of subtract or add, because we're going to have negative numbers in a bit. Okay? Yeah. So I really need to make sure it's an equation in your head, because you're going to have to subtract a negative number in a bit. Does that make sense? Okay. 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 Anybody have any questions?
Yeah.
Yeah.
So you first subtract the 2 from the helium, correct? You take the 2 from the helium and subtract that from the 95.
Yes.
Okay, and then the second step to that is the 4 on top of the helium, you subtract from the 241.
I mean, it doesn't matter what order you do them in,
Okay.
but it's literally that everything has to add up on both sides.
So they have to be the same.
They have to add up to be the same number on both sides. So when you have an equation, both sides have to add up to be the same thing, right? Okay. Okay. I don't want you to get into the habit of this is the process I have to follow every time, because sometimes you're not going to have to do anything with the mass,
No.
because it'll already add up to the same on both sides. Okay. Okay. So, I mean, this is literally just accounting, right? So if you just step back from this, you don't even have to think of this as chemistry. I have $95. I paid $2 out. How much do I have left? 93, right? I have $241. I pay out $4. I have $237. Very good. Okay. Okay, anyways, we're going to move on. And if we look on the periodic table, the 93 atomic number is what? Yeah, NP or neptunium. Okay. All right, so that is how you write out the nuclear equations. It is actually just as simple as they have to add up to be the same on both sides, right? So for the mass numbers, they have to be the same on both sides. For the atomic numbers, they have to add up to be the same on both sides. Okay? It's literally the same thing you would do with your bank account. Did Verizon charge me the correct amount this month? Okay? Maybe not. Beta decay. Now, this is why I was hesitating to say things like you always subtract and it's minus every time, is because beta decay is going to be where you lose a beta particle, and that's going to have a mass change of 0, right? No mass changes. It's going to have a charge change of -1, okay? Now, again, this does not need to be divided up into do this every time, because it's literally take the left side, add it up, take the right side, add it up, have to be the same, right? That's all you gotta do. So let's write the balanced equation for the beta decay of yttrium 90. This is actually used in cancer treatments and as a colloidal injection into large joints to relieve the pain caused by arthritis, in case you're curious. Okay, so we're going to be doing a beta decay of yttrium. So 90 over 39, y for the yttrium, right? Is everybody okay with why I do that?
Where's the 39 from?
It's from the periodic table.
Oh, okay.
So you look for the y on the periodic table. It's the atomic number 39. Okay, and so the next thing I'm going to do is, again, my mass here of 0, that doesn't change, does it? Okay, so I can just go ahead and write my mass over, 90. Okay, next thing I'm going to do is I have a 39 on the left side. For me to get a 39 on the right side, I have to take that and subtract off a negative number, don't I? Okay. When I subtract a -1, what does that do? Yeah, I'm going to have to add that, aren't I? So it's going to be 39 plus 1, right? That'll give me 40. Every time, if you're ever unsure of these problems and like, did I get this right? Just go back through and add both sides and see if it balances, right? That's all I gotta do. So over here I have 39. Over here I have 40 minus 1, don't I? That's 39. And so those balance. Cool. Okay, I'm going to look 40 at the periodic table. I'm going to find that symbol, and I'm going to put that down here. And so that is then ZR, isn't it? Or zirconium. Okay. Anybody ever heard of zirconium? No? Yeah, cubic zirconium, the fake diamonds. Not very popular anymore because there's the lab diamonds. Yeah. I don't know why anybody would bother with the cubic zirconium now. But so let's write another balanced nuclear equation for a beta decay of cobalt 60. So again, we're going to take that cobalt 60 as mass number 60, CO. We look at the periodic table. It has an atomic number of 27. And so that's going to then yield, well, we lost the beta particle, right? Beta particle, mass number 0, charge number -1. It's a high-speed electron. Okay, so how do I get these numbers for the next part? What's the mass number of my species I don't know?
So your mass number doesn't change.
Mass number doesn't change, so it's
60.
60. Very good. What would be my atomic number for that?
28.
Yeah, it's the 27 plus 1, right? 28?
Wait, why is it plus? This is minus right there.
Because they have to add to be the same.
So you have to do 27 plus the -1.
So remember, yes, you have to do the plus 1 in this case. But, okay, remember this is an equation. So if I had a problem that said 27 equals something minus 1,
And then you add that.
I'd add the 1 over, right?
So that's what we're doing here.
It's exactly the same thing.
Okay.
Yeah. Because remember, these are just equations. Yeah. They're solved the same way as a simple algebraic equation. Okay? Okay. They just have funny looking symbols. Oh, weird. I made a permanent 7 on my slideshow. I'm not sure how I managed that. Anyways, I didn't know I could do that.
And then the whole nuclear equation is that whole thing.
This is the whole nuclear equation.
Okay.
So we ended up with 28 before. We look at the periodic table. Yeah, that's nickel, isn't it? Ni. And so we put the Ni, and then we put it all together. Okay, so the next one's going to be a positron emission. When we're doing a positron emission, we're losing something with a mass of 0 and a charge of 1 plus, aren't we? Okay. And so, again, that will just have the positron right here. That's the positron, right? And that means your mass number doesn't change, but my atomic number is going to be 1 less, isn't it? Okay, gamma emissions, neither change. So it's a high energy nucleus. It loses a gamma particle that does not have any mass or charge. And so you end up with the exact same nucleus, just lower energy. Okay? It's literally as if you had a pile of stuff. It claps down and let out a sound. Okay? It's just sound doesn't exist at this small of a scale. And so it shoots off a gamma ray. Yeah?
Are you going to work out where the positron?
You don't need me to. If you need, you'll get practice.
Okay.
Yeah. Do the homework and get some practice. And it's literally just every single one of these problems is the exact same thing. You just top line, they need to add to be the same thing.
Okay.
Bottom line, they need to add to be the same thing. Okay, so this is a summary of these different radiation types in a nice, pretty way that has colors. Okay? So, ooh, ah, so beautiful. Okay, so let's talk about producing radioactive isotopes. So you may have wondered, I go in this hospital, there's like the nuclear floor, right? And then they have all these isotopes. Are they like searching the world for these isotopes all the time? No. No, they're definitely not doing that. Okay? What they're doing is they're taking a radioactive source. They're then shooting particles at a purified sample of something else. Okay? And when those compact, when they come together and they collide at high energy, sometimes those collisions will end up entangling them and create a new nucleus. Okay? And that's what you're seeing here. It's just the nuclear reaction where we've shot an alpha particle at a boron, and then that gives us our new radioactive nitrogen. Now, in most of these collisions, just like collisions with your cars, sometimes the collisions cause the cars to wrap up into each other, and they don't separate, right? But it usually causes some of the car to get going and fly off, right? Same thing here. We usually get a particle that flies off as well. Okay? Okay. By the way, does anybody know if there's anything radioactive that's seeping out of the ground under you right now? Anybody ever heard of radon? So in the United States, there's a pretty large part of the continent that seeps radon out of the soil. If you happen to make a basement or go into a crawl space, that radon gas tends to build up there unless you have proper ventilation. And that radon gas actually will get breathed into your lungs and will put off radioactive particles in your lungs. Yeah. And funny enough, every other state I've ever seen has very strict rules of testing for radon. Tennessee does not. Yep. They usually you test for it anytime you sell the property. Yeah, but for some reason Tennessee doesn't have it. Probably because there's not a lot of basements due to the water level. But okay, so let's write the balanced nuclear equation for the bombardment of nickel-58 by a proton. This is going to produce a radioactive isotope and an alpha particle. Okay? Okay, so I've told you 3 parts of this, haven't I? Fantastic. I have told you that we have a hydrogen coming in. This is combining with our 58 nickel, right? Okay. We look at the periodic table. Nickel has an atomic number of 28. Yeah. This is going to yield or equal out to something that I haven't told you, right? And then a alpha particle as well.
Wait,
Mm-hmm.
why is there the H on that side?
The hydrogen,
Yes.
You're adding
that is a proton.
And you're adding them.
Yep, you're putting nickel 58 and a proton together. Okay. And on the other side, that's going to give you the alpha particle and something else, right? Okay. Okay. So what we're going to do here is, again, we combine these numbers. So 1 plus 58 is 59. Very good. And now on the bottom over here, we have, we need to total to 59, right? So that is some number plus a 4, isn't it?
You don't add the 1 to the bottom?
We're doing the top right now.
Okay.
Yeah. We're just doing the top right now. We'll do the bottom a little bit later.
Okay.
Yeah. Otherwise, they'll get mixed up and we can't actually accomplish it.
Okay.
Okay. So how do we get that number right here that we want? 59 minus 4. Very good. Okay. And so that's going to be your 54, isn't it? So we'll put 54 here. Okay, so we take again on the other side, 1 plus 28.
That's 55.
Oh, is it? Oh, yeah, it is. Sorry.
You added the one from hydrogen.
Yep. No, you're good. Thank you. Okay, so 1 plus 28 is what? 29. Very good. And then we're going to subtract off what? 2. Very good. And that gives us 27. Excellent. Okay. So we look over at the periodic table for the 27. What species is that? Yep, cobalt. So it's going to be a cobalt with a mass of 55 and an atomic number of 27, isn't it? Okay. And yes, every one of these problems is basically the same thing. Okay. All right. So when we're measuring radiation, we're going to use what's called a Geiger counter typically. There's actually a few different ways of measuring radiation, but this is one of the more common ways you would see. This is a Geiger counter right here. Has everybody seen Geiger counters before? On like TV or something? Does he? That would be unusual. But
I've
that's...
heard he has a bunch of weird, like, military stuff.
Oh, then he very well may. Yeah. Yeah. Geiger counters are pretty common for military kits, depending on deployments and
He
stuff.
has those, yeah.
So what it composes of is it has a cylinder here, typically enclosed in glass. Inside of that cylinder, though you can do plastics and stuff as well, inside of that cylinder is actually a gas that ionizes very easily when it's impacted by radiation. Okay? Now, that gas is actually going to cause this, what's called a electrode in here, to detect whenever it's a positive or negative charge. Okay? And that'll cause electricity to flow. When the electricity flows, it's measured by this meter right here. And typically they go ahead and hook up a speaker to it so it makes little pops of sound every time something happens. Now, has everybody seen Geiger counters in movies and it goes pop, 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 and then it goes when it's really bad? And it's like, oh my god, I'm going to die? Yeah, that's Geiger counters, yeah. Or played video games. There's a very popular video game series, right? Anybody know what it's called? Fallout, yeah. Yeah. War never changes, of course. Okay. Yeah, show's actually pretty good. Okay, if you watch news, by the way, the Fukushima disaster also had a lot of Geiger counters on it. Okay. We'll go ahead and pick up here off of the next part of Geiger counters later. You all have a wonderful day. I will see you on Thursday.
Do we have lab this week?
Yeah.
Okay.
We have the Excel stuff.
What is the top?
We're doing the second part of that lab.
Oh, yeah, you're right.
Yeah.
Okay.
Yeah. Hey.
When are you putting in our test
Once I get everything, because that Friday thing messed up the people that were excused absences.
So not everybody's taking them yet?
Yeah, I got a couple people still out.
Okay.
And the other part is I need to grade them.
Okay.
And it is the damn machine does not actually take those deals. Why there's a Scantron sheet next to the Scantron that doesn't work with it, I have no idea.
Oh, well.
But
Okay.
yeah, take care.
Tomorrow I have your lab at 2:30, but I won't be able to come because I have a double header for the baseball team.
Okay.
Just wanted to let you know.
Sounds good. This week's lab specifically, you just need to use the Excel.
Okay.
If you have any difficulties with that or any of your measurements are messed up, you need to come and remeasure, talk to me, okay?
Thank you.
Take care, bye. Hey.
I cannot get this assignment done because I wasn't here, so not
Okay.
yeah,
That's fine.
yeah.
Um,
yeah, so the previous week before the assignment,
Yeah.
this one.
Okay. So, yeah, you missed the lab itself, didn't you?
Yeah.
Yeah, so what happens is there's actually a drop. So we have one drop and one makeup, okay? And so we'll do that as the drop, and then the next thing that happens, that it can be a makeup, okay? Okay.
Thank you.
No problem. Take care.
First of all, when is the midterm?
There isn't a separate midterm. There's just exam 1, 2, and 3.
Well, which one's coming up?
The next one will be exam 2.
And when's that?
Probably in like 3 weeks or so.
Oh, okay.
Yeah.
And I wasn't here for the clicker thing. There's my attendance not taken.
Oh, okay. Oh, you didn't get that one deal? Send me an email and remind me, okay?
Alright.
Okay.
Mm-hmm.
Did you have a laptop?
Yeah, I have a laptop.
Okay, you can do it with the laptop.
Okay, so
Okay.
should I send you an email?
So send me an email for today. Next time, laptop. Okay.
Oh,
Okay. Okay.